So in section 3 we're going to look at RSA and the regioselective synthesis of substituted benzenes, and we'll start by looking at synthons and synthetic equivalents. And with aromatic systems, the starting materials are usually benzene or a benzene derivative such as toluene, phenol or others, and the bond to be disconnected is almost always the bond joining the aromatic ring to the rest of the molecule. Normally the bond to the aromatic ring is broken to give a synthon with a negative charge on the aromatic ring, and this is because aromatic rings react with electrophiles in electrophilic substitutions. So if we're looking at disconnection of this bond between the benzene ring and the R group, we normally put the minus on the benzene ring, the plus on the side chain, and then our synthetic equivalent for the minus on the benzene ring will either be benzene itself, if we're looking at reactions with strong electrophiles, or something like a Grignard reagent if we're looking at reaction with relatively weak electrophiles. Important electrophilic substitution reactions include the following. So we've got bromination, nitration, sulfonation, Friedel-Crafts alkylation, and also Friedel-Crafts acylation. It's really important that you can remember these reactions when we're looking at forward syntheses. So we'll now look at electrophilic substitutions and regioselectivity. And for benzene rings bearing more than one substituent, you need to decide which bond disconnection to make first, and consequently which starting materials to use. So let's have a look at point 1. To decide on the order of disconnections, you must know whether substituents are orthopara, or 2,4, or meta, otherwise 3, directing. So let's have a look at a disconnection now. Here's my target molecule with a methyl group and a nitro group with a 1,4 relationship. If we now disconnect the carbon-carbon bond, put the minus on the ring and the plus on the methyl group, we now look at the forward reaction, and what we're looking at is methylation of what would be nitrobenzene. And as shown in the box here, the nitro group is a meta-director, so the substituent, the electrophilic group, would be introduced at the 3 position with regards to the nitro group. So that's an incorrect bond disconnection. The correct bond disconnection is shown here, where we cleave the carbon-nitrogen bond, and now when we put the minus on the ring and the plus on the nitro group, we're now reminded that of course in toluene the methyl group is orthopara directing. So we'll direct the nitro group to the 2 and predominantly the 4 position because of less steric hindrance, and so this will allow us to make the desired target molecule as shown in this scheme here. So toluene is nitrated to give a mixture of 4 nitrotoluene and 2 nitrotoluene. This is the major product, and we can separate these 2 regioisomers by distillation. If FGI is needed during the synthesis, it may alter the directing effect of the substituent, and the other substituent they may therefore be added before or after the FGI. So let's have a look again at a disconnection of this molecule, and we're going to look first at an incorrect bond disconnection. We cleave this carbon-nitrogen bond, minus on the ring, plus on the nitro group. Now we're looking at nitration of benzoic acid. The CO2H group is a meta-directing group, so it'll nitrate to put the electrophilic group at the 3 position of the ring. So now what we can do is in FGI. We can recognize that the acid group could be derived from a methyl group, and now we can cleave the same carbon-nitrogen bond, and we recognize that we can go back to this anion on the benzene ring, the synthetic equivalent of which will be toluene, and then you nitrate toluene as we saw earlier on, you could introduce the nitro group at the 4 position. So in terms of the forward synthesis, we nitrate toluene, we get predominantly the para-isomer, we need to separate it from the orthoisomer, and then in the subsequent step we can oxidize the methyl group to the carboxylic acid group. For point 3, we need to recognize that OH and OR groups are difficult to add to a benzene ring, so it's often a good strategy not to disconnect these substituents, but to use, for example, phenol as a starting material. So in this target molecule we have an OH and an NH2 attached to the benzene ring. We can't introduce an NH2 group directly onto the ring, but we can make it from a nitro group. So let's do an FGI first of all to go back to this 4-nitrophenol. Now we're going to cleave off the nitro group, a minus on the ring, plus on the nitro group, and the synthetic equivalents for this will be phenol and this nitrating mixture of nitric and sulfuric acid. So in terms of the forward reaction, we take phenol, we nitrate it, we We get predominantly a power isomer, we separate it from the orthoisomer, and then we selectively reduce the nitro group to the NH2 group using tin and HCl. For point 4, one strategy to improve the regioselectivity is to introduce a temporary blocking group, e.g. convert an NH2 group into a larger NHCOCH3 group. So here is my target molecule, this 4-bromoaniline. We're now going to do an FGI where we convert the aniline NH2 group into an amide, and the reason for doing this is this amide group is much more bulky than an NH2 group, and so it can direct the electrophilic substitution to give a higher degree of regioselectivity. We now cleave the carbon-bromine bond, we go back to the amide derivative, and then from the amide we can go back to aniline itself. So in the forward reaction we can take aniline, we can acylate it with ethanol chloride to make the amide group. We can then brominate it. We don't need to use FeBr3 in this particular reaction because this amide group is sufficiently activating, it will react with bromine itself. You make the 4-bromo derivative, and then we can convert the amide group back to the NH2 group. And it's interesting to note here that anilide is less, which is this molecule here, is less reactive to bromination than aniline. So polybromination is less problematic. Let's now look at Arrow-Grignard reagents and their use in the formation of carbon-carbon bonds. And Arrow-Grignards are formed by the reaction of aryl halides with magnesium in dry diethyl ether, or THF, because the Grignard would react with water, so we need to ensure there's no water that's present. And Arrow-Grignards are strong nucleophiles. They react with a range of electrophiles to form many carbon-carbon bonds. So this scheme shows some examples. We can react the Grignard with an aldehyde to form this alcohol on protonation. With a ketone, we now form a tertiary alcohol. With CO2, we form a carboxylic acid. With an ester, we can form this tertiary alcohol. With an epoxide, we can form a primary alcohol at the bottom left. And finally, with formaldehyde, we can form this primary alcohol here. So there's a range of different compounds that we can make here, starting from an Arrow-Grignard reagent. Let's now look at the use of this in synthesis with regards to 1-phenyl ethanol. We're going to disconnect the side chain from the benzene ring with a minus on the ring, a plus on the side chain. The synthetic equivalent for the minus will be a Grignard reagent. The synthetic equivalent for this, where we have a plus next to an OH group, will be an aldehyde. And of course we can make the Grignard reagent from the corresponding bromide. So we take bromobenzene in the forward sense, react it with magnesium to form the Grignard, react with ethanol, and then on acidic workup we form the desired secondary alcohol. We'll look at one other example now, 1-phenyl butanol. And again we're going to disconnect the ring from the side chain, minus on the ring, plus on the side chain. Synthetic equivalent for the anion will be a Grignard. Synthetic equivalent for this, we have a plus with 2 carbons, and the second carbon bears the OH as an epoxide. And the Grignard can be derived from the corresponding bromide. So in terms of the forward reaction, we take bromobenzene, we insert magnesium into the weak carbon-bromine bond, we react it with the epoxide, and you'll notice that we get regioselective attack at the least hindered position of the epoxide, and then on protonation we form the desired alcohol.